All right, let's get started. Section 4.4, the trigonometric functions of any angle. So up until this point, when we've done all of our sine, cosine, tangent, and cotangent, secant, and cosecant functions, we've been assuming, or at least in the last section, we were assuming that all of our angles for theta were in the first quadrant, meaning that the x and y coordinate points were going to be positive. But here's the thing, not all angles are in the first quadrant. So this section is chock full of information talking about how we can modify what we know about the 6 trigonometric functions and apply it to situations that have angles that are outside of the first quadrant, like the second, third, or fourth quadrants. So the key thing to remember is that to arrive at any of these particular trig functions, you're really kind of basing a lot of the originals, the sine, cosine, and tangent, off of that right triangle that I broke down for you before. And the right triangle was made up of 3 parts. The one side that was the x side, the one along the x-axis. Let me kind of illustrate this for you. Usually we were talking about a triangle that was like over here in the first quadrant. And there was a coordinate point up here we were talking about on the circle. This right here, this length is the x value in your coordinate, but it also happens to be the length of this bottom side. This side on the right was the y value, and this hypotenuse in the right triangle, which I drew a very curvy line, but it's really supposed to be a straight line, is technically the radius. Up until this point, when we were talking about the unit circle, we always called the radius 1. In this particular section, we're going to have situations where the radius is not 1. So instead of putting the 1 in for the denominator for the sine and cosine, and just calling them y and x when you take the sine or cosine of the angle, we're now going to have to factor in the radius of the circle, and we're going to divide y by the radius and x by the radius. And to determine the radius of your particular situation, we're going to be using basically the Pythagorean theorem just rewritten for r. A squared plus b squared equals what would have been c squared, but they took the square root of both sides, so now you've got this. And the one caveat is that you can't have a radius equal to 0. If you have a radius equal to 0, then you don't have anything. It's just the origin. It's not a circle, it's not an angle at all. So that's why they stipulate that it can't equal 0. So in most other cases in the trig functions, like tangent and cotangent aren't changing. Those are just what you're normally familiar with. Tangent of your angle equals y over x. Cotangent of your angle is x over y. But now secant and cosecant, instead of 1 over x and 1 over y, it's r over x and r over y, because you've reciprocated the y over r and the x over r. So let's take this and apply it to an example. Example 1. Let 7, negative 4 be a point on the terminal side of theta. Find the sine, cosine, and tangent of theta. So they're telling you right off the bat that this is your point that you're dealing with, your x and your y. And they want you to find the sine, cosine, and tangent of theta. The sine of theta in our situation here is not just the y value, but y over r. So in this case, we need to find the y value and divide it by the radius. And all we know to this point is the x value is 7 and the y value is negative 4. So to be able to find r, we're going to have to apply this modification of the Pythagorean theorem. R equals the square root of x squared plus y squared. And then we can use that to figure out what the sine of theta is and ultimately what the cosine of theta is going to be, and then the tangent of theta. Although really we can kind of jump right to tangent at the very beginning of this problem because we don't need the radius to find the tangent. The tangent's just y over x, and we have our y and we have our x. Our y is negative 4 and our x is 7. So There, we'll take care of that first because that's already done. Tangent of our angle in this case is -4/7. And for just making this look nice in my mind, I'm just going to write out the cosine right now so that we can work through this pretty quickly. All right. Radius equals x squared, the square root of x squared plus y squared. So let's substitute what we know. We know the x value is 7, the y value is -4. Let's plug them in, and then we'll simplify. 7 squared, don't need parentheses for that, but the -4 squared we will, because we don't want to make this a -16 in the end. We want the -4 multiplied by itself. All right, so 7 squared is 49, -4 squared is 16, 49 plus 16, that's 50 plus 16, which is 66, take away 1, which is 65. All right, that for our purposes is all we're going to do with it. If you could simplify this radical, we would do that. But 65, right now, that only has factors of 1 and 65, and then it's divisible by 5. I believe 65 divided by 5 is 13. So 13 is prime, 5 is prime. They don't have any perfect square factors. This is as simple as that radical is going to get. So now let's look over here. Y over r. Our r is the square root of 65, which 65 is real close to 64. The square root of 64 would be 8. So this is just a hair above 8 if we were doing the decimal version of it. But since we're not, we're going to leave it in radical form because we want to be exact. We need to take our y value, -4, and divide it by our radius, which is the square root of 65. However, we can't leave it like that. That's not in simplest form. We're going to have to rationalize it. I'm multiplying the numerator and denominator by the radical in the denominator. And that's going to simplify to give us -4 times the square root of 65 over 65. And that's as simple as that one's going to get, because 4 and 65 don't share any factors besides 1. So now, down to cosine to wrap up this example. We need 7 for our x value and divided by the square root of 65. And yet again, you're going to have this rationalization going on here. So once you've gone and multiplied that, you're going to have 7 times the square root of 65 over 65. And then you're finished. That is the answer to example 1. So, as I mentioned before, we're going to have situations where you're going to have angles that are not in the first quadrant. In your textbook on page 289, in the margin on the left side, they have these two little diagrams, and these are kind of here, I think, to help you visualize what's going on here. Last section and up until this point, for the most part, our angles were between 0 and 90 degrees, or 0 and pi over 2 radians, and so our x and y values were both positive. Okay, like everything in the first quadrant has positive x values and positive y values. So the first quadrant's going to have coordinates that are positive and positive for x and y. In the second quadrant, between 90 and 180 degrees, or pi over 2 and pi radians, your x values become negative, but your y values are still positive. So you may have situations where your angle produces a coordinate point, and that coordinate point is in the second quadrant, and they may tell you it's in the second quadrant, and then they're asking you to find the sine and cosine and tangent or something like that. And in this case, because the x value is negative, you're going to have cosine values that are negative, or even tangent values that are negative, just because the x value would be negative. I'll refer to this chart here in a second. Let me just finish off down here. Third quadrant, you've got negative x and y values between 180 degrees and 270 degrees, or pi and 3 pi over 2 radians. And then your x value is positive in the fourth quadrant, but your y value is negative. And that's between 270 degrees and 360, or 3 pi over 2 and 2 pi radians. So this is kind of handy, but I find that this is even more handy over here. It's kind of a shortcut idea here, where they're telling you, okay, in the first quadrant, all of your values are going to be positive. In the second quadrant, your sines are still going to be positive, but your cosines and tangents are negative. Third quadrant, your sine and your cosines are going to be negative, but your tangent's going to be positive. That's because tangent's equal to sine divided by cosine, and that's a negative divided by a negative, so that gives you a positive. And then down here, your sine's going to be negative because your y value is negative. Your cosine's going to be positive because your x value is positive, and negative divided by positive gives you negative. That's why tangent is negative. So I'm going to be referring back to this here in a second when we start looking at some problems like in example 2. All right, in example 2, here's our question. It says, given the cosine of theta equals 2/3. Okay, so we know the cosine of theta is equal to 2/3. All right. And in the last section, we talked about, and we did problems related to this. We used our trigonometric identities based on this particular statement to find out what other things equaled. So like, for example, if they said cosine of theta is equal to this, what's the cosecant? In the previous section, they always stipulated in the instructions that this angle was in the first quadrant. It probably didn't measure or didn't register to a lot of you because, I mean, it was just a formality. I think I mentioned in the last section that, okay, because it's positive, we don't have to think too much about it. It's just going to be, we're just going to use the trig identities to help you find the cosecant. But we're going to have to account for the fact that it may not be in the first quadrant now, and that's what this information right here is telling us. The tangent of theta is less than 0, aka the tangent of theta is negative. It's negative now. So that means, because the tangent is negative, it cannot be in the first quadrant, because the tangent's always positive in the first quadrant. In fact, what this information is telling us, because the tangent is negative, we're going to have to figure out, oops, I went to the wrong slide, which quadrant this is in, because that might have an effect on the cosecant. All right. But not only did they give us this information to figure it out, well, actually, let's look at this first. All right, the tangent is negative, so that means it can't be quadrant 1 because tangent is positive, and it can't be quadrant 3 because the tangent is positive there. However, now we're left with two possibilities. The tangent is negative in quadrant 2, and the tangent is negative in quadrant 4. So which quadrant is the angle in? Well, there's actually one other piece of hidden information in this problem. It's actually so hidden it's kind of staring you in the face, and that's this information here, which I butchered how I was circling it there. The information is that the cosine of theta is equal to 2/3, and 2/3 is positive. So the output of your angle, that when you take the cosine of it, is positive. All right. So what we have to do is look for when the tangent is negative and the cosine is positive, and that'll tell us what quadrant we are dealing with. All right. The tangent is negative, the cosine is positive. We are dealing with an angle in the fourth quadrant. Okay, so our angle is in the fourth quadrant. So, based on the fact that it's in the fourth quadrant, that might have an impact on our angle for our cosecant. Okay, we're going to need to look for find the cosecant here, and the cosecant, as we learned earlier, the cosecant is the radius over the y values. So the biggest impact here is the fact that we know we are dealing with the y value principally. The radius is always going to be positive. That's actually mentioned in the textbook. I didn't write it out here, but it should pretty much be plainly obvious that your radius is always going to be a positive length of line. So we're never going to attribute the whether the whole answer is positive or negative to the radius. If the answer is going to be positive or negative, it's going to be impacted by the x or the y value, where that coordinate is in the particular coordinate plane. So cosecant is dealing with the y value and the radius. And since we are dealing with a fourth quadrant situation, the fourth quadrant, the y value is negative. The x value is positive. So our cosecant is going to have a negative value in the end. All right, whenever we get around to writing our answer, the cosecant of theta, we need to make sure it's going to be negative something because it's in the fourth quadrant. So the output of our cosecant is something negative, right? Now that we've established that something is negative here, let's look at what they've given us here in this particular part up here, cosine of theta equals 2/3. All right, they told us that it equals 2/3, and we know the cosine is equal to the x value divided by your radius. So there's something we can kind of figure out about this, and that is that the radius must be equal to 3, and the x value must be equal to 2. Okay, so if we know our x value is 2, comma, something, we don't know the y value yet, and our radius is 3, the radius is actually involved in the cosecant. The cosecant is the radius over the y value. So that number is going to pop up again. It's going to be in the numerator of this answer. You're going to have the cosecant of theta equals -3 over something. We don't know what the y value is yet, but it's something. We're going to be using that to help us figure this out. So, given all of this, we now just need to find the y value. We can use this information in a few different ways. We could try going through the trigonometric identity method, trying to match up what's something that the cosine and the cosecant are paired with. However, we are actually dealing with a situation where we are still talking about any angle, and we can relate them using this particular equation, the Pythagorean theorem. Since we know the radius and we know the x value, we can find the y value. And we know the y value's got to be negative, so it's not going to impact our output here. Whatever we get, even though when we're going to square the y and take the square root, and that would normally give us a positive output, we know what the y value is going to be, and it's just going to be the negative output of this. So let's plug in what we know. We know that 3 is the output, and we know that that's going to equal the x value squared plus the y value squared, and we just don't know what the y value is. So we're going to do a little bit of simplifying here. All right, this 2 squared is 4. And then we're going to have to solve for y. We're going to have to square both sides, making this 3 and 9. We're going to have to subtract the 4, making this a 5. And then we're going to have to take the square root of both sides. Now, normally when you take the square root of both sides, you would put a plus or minus here. So it could be plus or minus, but we know our y value has to be the negative version. So we're going to be dealing with the negative square root of 5, and the negative is already written over here. I'm just going to write the square root of 5 here. And the only step that we have left here is to rationalize. We've got to multiply the numerator and denominator by the square root of 5, and that will lead us to the solution we are looking for. So 3 times the square root of 5 is going to be 3 square root of 5, and then the square root of 5 times the square root of 5 is the square root of 25, which is just 5. And that's our solution for example 2, -3 square root of 5 over 5 for the cosecant. Okay, now example 3, evaluate the cosecant and cotangent functions at 0 and pi over 2. Okay, Now, 0 and pi over 2, these are quadrantal angles that we talked about back in the last section, aka they are angles that fall on the quadrant lines, the lines that break or separate two different quadrants. So we're not going to be relying on these charts for the sine, cosine, what have you, because they're going to fall on the lines. So if we're trying to find the cosecant of our angles 0 and cotangent at 0, I shouldn't have written it so far below. And then we're going to need to find our cosecant at pi over 2 and our cotangent at pi over 2. All right, cosecant is radius over y value. So if we're looking at this, they tell us that we are dealing with a 0-degree angle. A 0-degree angle has an x value and a y value of 1 and 0. If you go and plug this in, we're going to need to find the radius over the y value. The radius is equal to the square root of the x squared plus y squared. And we know our x squared is 1 squared, and our y squared is 0 squared. 1 squared plus 0 squared, 1 times 1 is 1, 0 times 0 is 0, 1 plus 0 is 1, the square root of 1. Your radius is just going to be 1. And then the y value for the cosecant at 0 is 0. So guess what happens? 1 over 0, this is going to be undefined. Can't divide by 0. Cotangent. Cotangent is a little bit easier because that's just going to be the x value divided by the y value. So going back here, the x value at 0 is 1, and the y value, let me write in x over y here. We get 1 divided by 0 again. So guess what? It's undefined as well. All right, cosecant of pi over 2. Again, radius over y value. For pi over 2, your radius is going to be, we're going to have a similar situation. At pi over 2, you have 0, 1 as your coordinate point, so we're going to plug this in. 0 squared is 0, 1 squared is 1, 0 plus 1 is 1, and the square root of 1 is 1, so your radius is 1. The only difference this time is the cosecant for this one relies on the y value, 1 over 1, so you're actually going to get an answer for the cosecant of pi over 2. You get 1. The cotangent, again, is x over y. So x divided by y, that's 0. Let me make that look better. 0 divided by 1. So you're just going to get an answer of 0.